Hello everyone. In continuation of my earlier lecture where I discussed the various speeds that can be associated with a gas molecule based on the assumptions of the kinetic theory of gases and the Maxwell's law of distribution of speeds, today I introduce to you the concept of the mean free path. Mean free path is denoted by the symbol lambda first. Always remember. Always we use the symbol lambda to denote what is the mean free path. What is the physical significance of the mean free path? How to calculate the mean free path? And where is it applied? That is very important to understand in this lecture. Now, why does and how does the concept of the mean free path originate? In elementary kinetic theory, gas molecules are considered as point masses and intermolecular collisions are ignored. Now everybody knows this because these are the basic properties of an ideal gas and the kinetic theory is applicable for ideal gases only. To explain the finite time taken by a gaseous mass in an open container to disperse, Clausius assigned a finite size to the gas molecules. Now what did Clausius say? Clausius said that when a molecule moves within the gas under equilibrium conditions, it necessarily collides with other molecules. It encounters in its path and undergoes frequent change in the direction of motion. Not only does it undergo change in the direction of motion, it can also undergo a change in the magnitude of its speed. This results in a series of zigzag paths. Each zigzag path is called a free path. And remember, the free paths are of unequal length. They don't have equal lengths. Some are short while others are long. The average length of the free paths is referred to as mean free path. Thus, the mean free path is the average distance travelled by a molecule between two successive collisions. Very important. This is the distance travelled by one molecule between two successive collisions. It means while traversing a distance equal to the mean free path, the molecule doesn't encounter or undergo any collision. We denote it by the symbol lambda. Now let us calculate the expression for mean free path. If lambda 1, lambda 2, lambda 3 and so on so forth lambda n are the successive free paths traversed by a molecule in time t and n denotes the total number of collisions suffered in this period. Then we can write lambda as lambda 1 plus lambda 2 plus lambda 3 plus so on so forth plus lambda n divided by n. If v is the average speed with which a molecule moves in the body of the gas, then we can write lambda as Vt by n. Here we have used the simple expression velocity is equal to distance over time. So distance is velocity into time. Under normal conditions, the mean free path of oxygen molecules is about 2 into 10 to the power minus 7 meters. This is smaller than the wavelength of the visible light, which is in the range 4 into 10 to the power minus 7 to 6 into 10 to the power minus 7 meters. However, the mean free path is greater than the average intermolecular separation given by 3 into 10 to the power minus 9 meters. Let us consider two particles of radius r. In order to undergo collision, the centers of the two particles of radius r must approach to within a distance given by d equal to 2r. The picture on the next slide illustrates this point. Two molecules are shown in brown. They are approaching each other. The distance between the two centers is given by d. D is equal to 2r, and the dotted circle is referred to as the sphere of exclusion, as you will just see. Let us assume that the molecules are spheres of diameter d. We will see on the figure on the next slide that no two molecules can collide unless their centers are less than a distance d apart as they approach each other. The radius of the sphere of exclusion, which is represented by the dotted sphere, equals the molecular diameter d. So, sigma is equal to pi into d square. D is the diameter. Now, in this figure, you can see a brown colored sphere and a blue colored sphere on the left hand side of the slide. On the left hand side, you see the brown sphere is approaching the blue sphere. These two spheres are representing two different gas molecules but having the same diameter d. And this is representing the actual collision that is occurring. On the right hand side, we can see a bigger blue sphere and a smaller brown sphere, which is referred to as the equivalent collision. Now, what is the equivalent collision? You will understand in a few moments. So, description of figure: we have two spherical molecules, each of diameter d. They collide if their centers are within a distance d of each other. The collision between the two molecules is equivalent to a point molecule colliding with a molecule having an effective diameter of 2d. An equivalent way to describe the collisions is to imagine that one of the molecules has a diameter 2d and the rest are the geometrical points. It means the sphere in blue has a diameter 2d and the brown sphere is simply a geometrical point. It means it is a point mass. Let us choose the large molecule to be the one moving with the average speed v. In a time t, this molecule travels a distance vt. Again, we have used the simple expression velocity is equal to distance over time. So, distance is equal to velocity into time. In this time interval, the molecule sweeps out a cylinder having a cross-sectional area given by pi d square and a length vt. So, the length of the cylinder is vt and the cross-sectional area is given by the area of the circle given by pi d square. So, this figure is showing the circle, the cross-sectional sphere and the cylinder of length vt. In a time t, a molecule of effective diameter 2d sweeps out a cylinder of length vt where v is its average speed. In this time, it collides with every point molecule within the cylinder. Hence, the volume of the cylinder is pi d square Vt. If n is the number of molecules per unit volume, then the number of point size molecules in the cylinder is given by pi d square Vt into n. Here pi d square is the cross sectional area of the cylinder, Vt is the length of the cylinder, and small n is the number of molecules per unit volume. Always remember, small n is the number of molecules per unit volume and capital N is the total number of molecules. The molecule of equivalent diameter 2d collides with every molecule in the cylinder in the time t. Hence, the number of collisions in the time t is equal to the number of molecules in the cylinder, which is given by pi d square into Vt into small n. The mean free path equals the average distance travelled in a time t divided by the number of collisions that occur in this time. So, hence to find out lambda, we should divide distance travelled Vt by pi d square Vt into n, that is the number of collisions. Simplifying the expression, we get lambda is equal to 1 by pi d square n. This is the Clausius expression for mean free path. Mind you, in this expression, a very important assumption has been taken. The assumption is that only one molecule is moving and the rest are stationary. Since the number of collisions in a time t is pi d square Vt into n, the number of collisions per unit time or the collision frequency f will be given by pi d square V into n. The above expression is not exact and has some errors because it is based on the assumption that only one molecule under consideration is in motion while all others are at rest. This is not true. The kinetic theory says that all the molecules are in continuous random motion. If the motion of all the molecules is taken into account, the corrected formula for the mean free path becomes lambda is equal to 1 by root 2 pi d square n. So, correction factor of root 2 is taken in the denominator. Pi is a constant, d is the diameter. Always remember students, this is a very common mistake taken. D is the diameter and not the radius, and small n is the number of gas molecules per unit volume. It is not the total number of molecules. The inverse of the collision frequency is the average time between collisions, known as the mean free time. Our analysis has assumed that molecules in the cylinder are stationary. When the motion of these molecules is included in the calculation, the correct results become divided by root 2. Now, let us see, mean free path is such an important parameter while understanding the kinetic theory of gases. So, on what factors does the mean free path depend? From simple gas law, we have equation of state, we have PV is equal to RT. Let us divide both sides by the Avogadro's number. We then have PV by Na is equal to RT by Na. This means that P is equal to small n into K into T, where small n is Na by V and K is R by N is the Boltzmann constant. Here again you can see small n is the number of molecules per unit volume or the Avogadro's number per unit volume, which means that small n is equal to P by kT. If we substitute the value of n in the expression for mean free path, then the expression for mean free path becomes lambda is equal to k into T by root of 2 pi into d square into P. So this expression enables us to find out the factors which affect the mean free path. Let us discuss each factor in detail. The first factor that affects the mean free path lambda is the density. Very, very important. Density is inversely proportional to the mean free path. Why? Because on increasing the density, what happens? The molecules come closer and start colliding more often. That is, the number of collisions increase. Thus, it decreases the mean free path because the number of collision is occurring in the denominator of the expression. If that increases, the mean free path has to decrease. In the same way, on decreasing the density, the collision decreases. This leads to an increase in the mean free path. The second factor which affects the mean free path is the number of molecules. This is very, very elementary and very, very evident also. The number of molecules is also inversely proportional to the mean free path, because if we increase the number of molecules, the number of collisions increase. The number of collisions is occurring in the denominator of the mean free path. Therefore, the mean free path has to now decrease. I hope this is clear. The third factor that affects the mean free path is the radius of the molecule. Very important. The increase in the radius of the molecule is inversely proportional to the mean free path again. The increase in radius increases the surface area of the molecule. Due to it occupying the space, it can touch the neighboring molecules and decrease the effect on the mean free path. Now we come to the very, very important parameter which affects the mean free path, that is the pressure. How does the mean free path depend upon pressure? The mean free path lambda is inversely proportional to the pressure. In other simpler terms, we can say on increasing the pressure, the mean free path decreases. How does the mean free path depend upon volume? The mean free path is inversely proportional to the volume too. What does this mean? On increasing the volume, the mean free path decreases. How does the mean free path depend upon temperature? The temperature is directly proportional to mean free path. Mind you, pressure was inversely, temperature is directly. As soon as we increase the temperature, the kinetic energy increases. This leads to the faster motion of molecules. Let us illustrate this point by solving a problem. What is the problem? If the mean free path of a molecule is given as 1.5 into 10 to the power minus 10 meters, find out at what temperature in pascals is the molecule travelling at 2 atmosphere when the diameter of the molecule is given as 1.2 into 10 to the power minus 6 meter. So what is given in this problem? Lambda is given. What is lambda? Lambda is 1.5 into 10 to the power minus 10 meters. Pressure is given 2 atmosphere. Diameter is given 1.2 into 10 to the power minus 6 meter. So first of all, we convert atmosphere into pascals. So converting it, we get 2 into 101.3 into 10 to the power 3 pascals. We could have written it as 2 into 1.013 into 10 to the power 5 pascals also. So lambda is now given by kT by root 2 pi d square p. Substituting the various values, we get 1 by t as 1407.909 into 10 to the power 4, which gives us T equal to 7.10 Kelvin. Let us again illustrate by concentrating on one more problem. The problem states the mean free path of the molecules of a gas at pressure P and temperature T is 3 into 10 to the power 7 meters. We have to calculate lambda if the temperature is doubled and the pressure is doubled. So we have two parts to the problem. In the first part, the temperature is doubled, and in the second part, the pressure is doubled. We already know that lambda is equal to kT by root 2 pi d square p. When the temperature is doubled, the mean free path will increase by a factor of 2. Hence lambda p comma 2t. It means lambda taken when pressure is taken as p and temperature is taken as 2t. It is not lambda into p into 2t. It is simply written as that lambda is considered when pressure is taken as p and temperature is taken as 2t. This is equal to 2 times lambda p into t if we see the expression above. So what do we get? Lambda is equal to 6 into 10 to the power minus 7 meters. So when the pressure is doubled, the mean free path will be halved. So lambda when p is taken as 2p and t is taken as t, we get lambda by 2, which is 3 into 10 to the power minus 7 meters. Next, let us discuss what is the distribution of free paths. How does the free path vary? Let us consider a molecule at the start of the journey, that is point O. Let us assume that the past history of the molecule does not influence its subsequent motion in any way. Suppose that a molecule moving with average speed v is travelling a distance OA equal to x without suffering any collision. The probability of this event will be a function of x. Let us denote it by fx. The probability that this molecule makes a collision in moving from A to B will be determined by the product of the collision frequency and the time interval in which it covers the given distance. So this figure is showing that a molecule is travelling from O to A without colliding with another molecule. It traverses a further distance AB in time dt. This further distance is dx. It's a small distance in comparison to x. So we can take it to be equal to Pc dt, where Pc is the collision frequency. Since dx is equal to v into dt, we can now write Pc dt is equal to Pc into dx by v. which is equal to dx by lambda. Lambda is the mean free path, dx is the additional distance travelled in time dt, Pc is the collision frequency, and we have to now find out the distribution of free path. Hence, the probability that a molecule traverses a distance dx without making a collision is now 1 minus dx by lambda. The motion from O to A and from A to B can be considered as two independent events. The probability fx plus dx of this molecule completing its journey from O to B without making any collision is equal to the product of probabilities for individual events. Mathematically, we can express it as fx into 1 minus dx by lambda. Hence, we can write fx plus dx is equal to fx 1 minus dx by lambda. Using the Taylor series expansion and ignoring second and higher order terms, we can get dfx by dx is equal to fx by lambda. Integrating, we get fx is equal to a exponential minus x by lambda. We can find out the value of a by using the fact that f0 is equal to 1 and we say a is equal to 1. So, we get fx is equal to exponential x minus lambda. This is the law of distribution of free paths, and it suggests that the probability of a molecule travelling very large distance without making a collision will be vanishingly small. So, we will discuss if we have a sample of n naught molecules in the beginning, what will be the number of molecules left after traversing a distance x in my next lecture. I hope the things are clear, the significance of mean free path is clear, the expression derived from mean free path is clear, and in the subsequent lectures I will discuss with you other various important concepts related to the kinetic theory of gases. Thank you.